is Abhay Pasupathy, and I work at the Department of Physics at Columbia University. And I run an experimental group, which means I don't actually do any work. So all of the work that I'll describe today is done by the following people mostly, and I'll acknowledge a few collaborators at the end of my talk. The majority of the work is done by my graduate student, Drew Edelberg, who will graduate fairly soon. And some of the work on magnetism is done by a slightly less senior graduate student, Alex Kerelsky. I'll talk about some measurements that are done using muons, and these are done by Zurab Gugucia, who is with me right now, but will soon move to PSI in Switzerland. He has a position there. And I'll talk a fair bit about TMD crystals, and these TMD crystals are grown by Dan Rhodes, who works at our MRSEC at Columbia. So I work at the Columbia University Physics Department, and this guy, for those of you who don't know who this guy is, this is Rabi. Rabi is one of the big dudes in the Columbia Physics Department. He's difficult to escape. His picture is everywhere, and his name is everywhere. And so I was, when I came in, I said, I should find out what Rabi thought about the things that I'm doing, and here's the best thing that I found from the 1960s. So at the time when people were studying silicon, I guess, Rabi made this famous statement, at least in the Columbia Physics Department, which says that my department, that is the Columbia Physics Department, will have nothing to do with the physics of dirt. So that's all I could find about Rabi. But then another wise person said the following thing, which I really believe in, which is defects in materials, like in people, make life interesting. I think this is especially true of semiconductors. Without defects, you have nothing. Semiconductors are very boring without defects. I think this wise person was me. I just made that up. Okay, so I'm actually going to confine myself to only this class of semiconductors in my talk. These are the famous transition metal dichalcogenide semiconductors. And I like this slide because it tells you a lot about various members of this family just by looking at very simple chemistry. So these transition metal dichalcogenides are of the form MX2, where M is molybdenum, tungsten, can be niobium, or any transition metal. And X, the chalcogen, is sulfur, selenium, or tellurium. I'm going to particularly look at the 2H form, where the metal atom has a triangle of chalcogen atoms on the top, and a triangle oriented the same way, the so-called trigonal prismatic version of these compounds. And if you take a metal ion and you put it in this coordination, just from sort of symmetry principles, the d orbitals of the metal atom are going to split up into 1, 2, and 2 in this particular way because of the crystal field. And then you have to just ask, which metal atom do you have here to understand whether this material is a metal or a semiconductor. So for example, if you put niobium, which when all said and done, niobium 4 plus is in a 4d1 configuration, that means I have one electron in this lowermost d orbital. And so it's a half-filled d orbital, and you expect this to be a metal. Whereas if you look at the ones that I'm going to talk about today, MOS2, MOSE2, and so on and so forth, the molybdenum in this particular case is in a 4d2 configuration, and 4d2 is going to fill this lowermost d orbital. And so just from this very simple picture, you expect this thing to be a semiconductor. And this is somewhat important when it comes to magnetism. I'll come back to this picture in a second. Okay, so the next important thing that I want to talk about is to distinguish. I'm going to talk about defects. And so we should ask, for a two-dimensional material, there are in general two types of defects that influence the properties of a two-dimensional material. One is, if I take a two-dimensional material, this is graphene, you can create a defect inside the crystal lattice. So this is one of these defects. In this particular defect, the 6-membered carbon rings are broken into 5-membered and 7-membered carbon rings. This is called the Stone-Wales defect. Now, as it turns out, in graphene, these are extraordinarily rare. If you take a piece of graphene that's 1 micron square, on average, you have 3 to 4 of these defects. So for all practical purposes, people have just ignored them. Graphene is sort of a perfect material. Now, if you have a two-dimensional material, it's also significantly affected by the environment, by the substrate it sits on, for example. And so in the business of graphene, all of the work has gone into making one perfect sheet of graphene in whichever way possible be as ideally isolated from the environment as possible. So this is some beautiful work encapsulating it with boron nitride done by Jim Hone and Corey Dean and so on at Columbia. But when we come to these newer materials, the transition metal dichalcogenides, it's a very good question to ask, is this same assumption true? Can we just neglect all of these intrinsic defects that might exist in the material, just worry about extrinsic disorder? Right? And I hope to show you that this is not the case. Now, as it turns out, the way the field has gone, the field has tried to borrow the same things that you do in graphene by encapsulating in boron nitride and so on and so forth, and have mostly forgotten that there's also defects that exist within the material itself. But that's just, that's the way fields go. When you do something new, you just look and see what's been done before and you try to copy it. That's the way we do things. Okay, so with those preliminaries, let me get to an outline of what I'm going to tell you today. So first, I'm going to tell you a little bit about how these materials are grown, these transition metal dichalcogenides. And I'm going to do a very simple count of defects. I'm going to grow a material. I'm going to ask how many defects exist in this material. And then we'll dig in a little deeper. I'll try to identify what types of defects exist in these materials. And I'll tell you what the electronic properties of these defects are. If you are a person who does something other than what I do, which is microscopy, then you're interested in other properties like transport properties or optical properties. And what you care about at the end of the day is how these defects affect what you measure. And I'll show you that at least in the case of optical properties, these defects can have dramatic effects. And then the final part of what I'm going to discuss today is something we found quite by chance. We found that these defects also have interesting magnetic properties. I'll spend a little bit of time on that as well. Okay, so let's get right into it. Let me tell you how these materials are grown and what types of defects are produced when you grow them. So the transition metal dichalcogenides are actually a very, very old class of materials. These were being grown in the late 60s. And in those days, people were growing bulk single crystals of these materials. And even today, people grow bulk single crystals of these materials. So this is sort of a well-known and well-established route for now 50 years. The new part of TMD research is, of course, Scotch tape. We've learned how to use Scotch tape productively since about 15 years ago. And now we can take these bulk crystals and exfoliate them down and make single layers of these materials. There's also been tremendous progress in the last 10 years or so where you can actually directly grow single layers of these materials. So this is just a picture with my local bias. This is work done at Columbia, but I believe you'll hear some of this even at this conference. There's now many different methods, chemical vapor deposition, MOCVD, PVD, so on and so forth, where you can directly grow one layer or two layers of these materials on lots of different substrates. And this sort of has really revolutionized many applications of these materials. Good. Now, in terms of defects that you can have in these materials, since you have a two-dimensional material, we can broadly classify defects into two types. Defects can either be a one-dimensional defect. So shown here is a grain boundary. What you can see are defects in the atomic positions. And this form a one-dimensional line, and these grain boundaries can stitch together in many interesting ways. You can also have point defects. So shown here is one particular point defect where there's a hole in the material just at one single point. So point defects and grain boundaries. So when I got into this, there's this whole range of different materials that can be produced. There are all these different defects that might exist in these materials. And I had to tell my students something to go study something concrete. So here's what we decided. What we knew is that if you did transport or you did optics, then the highest quality samples that people use today are still samples that are exfoliated from bulk single crystals. So we said, well, for now, let's stick to these bulk single crystals. The two-dimensional growths are fascinating, but we won't focus on this for now. These exfoliated bulk crystals in general don't have grain boundaries. So if I look at a crystallite of one of these things, they have no visible grain boundaries. And so we said, for now, let's not worry about these line defects. All we'll talk about is point defects. Now, let's say you want to study these bulk crystals. You need to get your hands on some of these crystals. And so you have essentially three options. One is some of these are naturally occurring. You can mine them. So we said, no, we're not mining anything. You can buy them. There's a number of companies that will sell you single crystals of these materials. So we bought a few of these. And then eventually, it turns out to be not that difficult to grow them. So we grow, these days, the best crystals ourselves. Now, we had a very simple question. Let's say you buy a crystal. You go to a company. I won't name any companies. You pay them $500, and they'll sell you some crystals. I'd like to ask them a question. How many defects are in your crystal? The answer is, we don't know. That's the state of the art. The state of the art is if you get a bulk crystal, your guess is as good as anybody's as to how many defects that thing has. And you'll also ask anybody, including myself, everybody will say, ours are good. We don't know about other people's, but ours are good. So we said, well, that looks like a problem that one should address. One should know if I have a typical crystal, how many defects do these things have it? So that's what we set out to do. And the way we do it is to use scanning tunneling microscopy. That's the technique that's most used in my lab. And we go down to atomic resolution so we can see these individual defects. And we also work with scanning TEM people where we can see the same defects from a more structural perspective. And one of the things, so this has taken us now a good 2 years to do. And one of the things we faced was there's actually a fair amount of literature. If you just Google defects in transition metal dichalcogenides, you'll see many beautiful pictures like this. You'll see defects of many different types in many different papers. The problem is that in the field, as far as I can tell, people have not been really systematic about what you're doing. So what you do is you pick a particular material that somebody made, you find some interesting defects, and you write a paper about it. But this is perhaps not the most useful thing if you're a materials grower. You want some clear directions on how should I grow my materials so they minimize the defect count. And so what we wanted to do is to be systematic and sort of go through different ways of growing crystals and come up with some generic statements. So after all of our work, we've now settled on two techniques, which are sort of the two most adopted techniques for the transition metal dichalcogenides to make bulk crystals. So the first technique is called chemical vapor transport. In this, what you do is you have some precursor materials. These precursor materials are heated on one end of a hot tube. And then you have another end of the hot tube, which is slightly cooler. And the hot stuff will sublime. It will be carried over by a transport agent. And it will go and condense on the other side and produce crystals. And if you buy crystals, this is the method by which they grow these crystals. And you can get nice big, centimeter-sized crystals by this method. Now, more recently, since we've not been super happy with this growth method, we've been growing crystals using a flux method. And a flux method is basically growing crystals like how you would grow sugar crystals, for example. You have a flux. In this particular case, it's the chalcogen itself which acts as a flux. And then you seed a little crystal, and you just let it grow, and you let it get bigger over time. So that's the second method that we've adopted. And at the end of the day, we have nice shiny crystals, and we want to study them in as pristine a form as possible. So we put them in a UHV chamber. We cleave them in situ so that we have no external impurities, and we come down with an STM tip, and we want to see what kinds of defects we have. So a little bit more about the sample growth. So the CVT process typically takes on order of a week to do if you want to do a good job, make the highest purity crystals, whereas the flux method typically takes about a month or a couple of months. So if you're a company, they don't really like to do this because it takes a long time. You can grow fewer crystals. Good. So let me get straight to the data. So this is molybdenum diselenide, and we've studied a few different versions of the TMDs. On the left here is a CVT crystal grown by chemical vapor transport. On the right is a flux crystal. And these are cleaved surfaces. So if I had no defects, this surface would be absolutely flat. But indeed, you see that it's not flat. You see those little points that are defects. And as I'll show you in just a second, each of these points is one individual atomic defect. And so what I can do is I can just look at the total number of atoms in this image. I can count the total number of defects in this image, and I make a defect count. Very simple. And for this particular material, if you look at the defect count, it's about 2.5 times 10 to the 12 defects per square centimeter. In other words, this is on between 0.1 and 1% of sites are defects, which is an absolutely enormous number. So this is now with our improved technique, the flux technique. We do the same thing. We can get a defect concentration that's about an order of magnitude better. So we can get down to 1.7 times 10 to the 11. That was MOSE2. This is WSE2. Do the same thing. CVT WSE2 has just a boatload of defects. It's 5 times 10 to the 12. And flux WSE2 is actually the best crystal we've ever grown. These are sort of best that I've ever seen in anybody's crystals, are on the order of 10 to the 10 defects per square centimeter. We are still about 2 orders of magnitude away from graphene, but 2 orders is better than 4 orders, which is what it was earlier. Good. So here is the takeaway message from this. You can grow crystals by 2 methods, CVT and flux. Flux produces better crystals. And for the best crystals, we are down in the 10 to the 10 defects per square centimeter range. And now what I want to do is I want to zoom in around these individual defects and ask, what are these defects in these materials? Okay. So here's now a zoom in. You can start to see the lattice. And these are the chalcogen atoms on the surface. And if you zoom in, you'll see that all of the defects that we see with greater than 99% probability fall into what we call the dark defect here and the bright defect there. And these bright defects are always centered on the chalcogen site. The dark defect is always centered between 3 chalcogens, so it's centered on the metal atom. And let me just tell you what we think these are. So I should say that in STM, we don't have any chemical specificity. So we have to use other things in order to help us understand what these things are. But let me tell you what these things are, and then I'll explain why. This thing we believe is a metal vacancy. It's just a missing metal atom. And this thing we believe is an anti-site defect. An anti-site defect is where there should be a selenium atom, but instead of the selenium atom, there's a metal atom sitting there. We've done the same thing for WSE2. And once again, we see the same 2 defect types. Same story as before. Now, as far as the vacancy goes, the metal vacancy, what we can do is we can take this material, we can exfoliate a single layer, we can put it in a TEM, and we can just look for metal vacancies. Metal vacancies are not all that difficult to see in a good TEM these days. And so here, this is a big TEM image of one of these monolayers of WSE2, and there you see metal vacancy. And so what we've done is we've characterized samples with STM. We've given them to our TEM collaborators. They study the same material. They see how many metal vacancies there are in these materials. And it matches pretty well with what we see in the STM. So we're pretty happy about that. Now, the anti-site is somewhat trickier to see in TEM, so at least with the TEMs that we have. And so what we know from STM is that we don't have a missing chalcogen atom here. We don't have a chalcogen vacancy. In fact, in the literature, if you read the TMD literature, everybody talks about chalcogen vacancies. In our 2 years of scanning these things a million times, we've probably seen 3 chalcogen vacancies. There aren't any chalcogen vacancies. But these things are a defect on the chalcogen site. And what we believe is that during growth, you can actually have a metal atom pop in instead of the chalcogen. And once the metal atom pops in, it's fairly happy to be there. And so we worked with our ab initio theory collaborators, where we said during the growth, you can have a chalcogen vacancy. So this is a chalcogen vacancy during growth. This chalcogen vacancy is sometimes, on occasion, filled up by a metal atom. That metal atom could come from a neighboring metal atom, or it could come from a metal atom in the melt. If, for example, it comes from a neighboring metal atom, you now have a metal vacancy, and it's quite easy for that metal vacancy to drift away. And so what you're left with is this anti-site. And once this anti-site is formed, it's actually reasonably happy to stay in this material. It's not too bad. So that's sort of our picture for what the anti-site is. Good. Okay, so here's a summary of this part. So what we see primarily are two defect types. One is the metal vacancy, one is the chalcogen anti-site. And depending upon the growth method, the numbers of these don't necessarily have to be 1-to-1. So in our very best crystals, we have only this type of defect. And as the defect quantity gets higher, we see more and more of the anti-sites. Fine. So we've seen what these defects are. And one of the things you can do in STM is you can go down, and with atomic resolution, you can measure the spectrum on these defects and ask, what do these defects look like spectroscopically? So that's the next thing we went ahead and did. And a little primer on STM spectroscopy. So what you do with an STM is essentially an IV measurement. You sit at a particular point in space, and you change the voltage, and you measure current. And if you do this for a semiconductor, this is for just the same material, molybdenum telluride, that I'm going to tell you about. What you measure is a spectrum that looks like this. And this is the valence band. This is the conduction band. On both sides, you have states available for tunneling. And between the valence and conduction band, you have a band gap. That's the band gap of the material. And if you have defects, you can have states. These states can either be in the bands themselves, or the states can be inside the gap. If we go to the metal anti-site and we measure carefully what the spectrum looks like on the metal anti-site, we see this nice little additional state that exists on the edge of the conduction band. And so a state that's on the edge of the conduction band is a donor state, if you remember your semiconductor physics. And we can characterize how far away from this defect this state exists. It exists about 3 nanometers away, and if you go 3.5 nanometers away, the impact of the state is gone. We can do the same thing on the metal vacancy. So here is the metal vacancy. And in this case, you see a nice state. Now this state is close to the edge of the valence band. And once again, about 3.5 nanometers away, the impact of this state as well is gone. So the metal vacancy acts as an acceptor, and the chalcogen anti-site acts as a donor. And if you think about what these things are chemically, if you think about it for 5 minutes, you'll realize that this thing makes sense, this assignment. Good. Now, what we can also do is I can go to every point in my crystal, and I can measure the band gap that you see in STM. And in the vicinity of that defect, the band gap is slightly changed. And what I'm showing here on this upper left-hand corner is a plot that measures what the band gap is at every point in space. And the size of this image is 500 nanometers. And we chose 500 nanometers because that's a typical diffraction-limited optical spot. So if you have an optical spot that's at your best resolution, you're averaging over this area of the sample. And this is what, locally, this is what the gap of the material looks like. It varies from about, in this case, 820 millivolts to about 900 millivolts. This is for one of our crystals that's not the best, the vapor transport grown crystal. This is on the flux crystal. And if you look at the contrast in this image and the contrast in this image, you can see that this one has much less contrast, telling you that the gap in space is much more uniform. You can also just take a histogram of these gap values. So here is a histogram for the CVT sample. Here is a histogram for the flux sample. Once again, you see that the histogram for the flux sample is just much tighter than the histogram for the CVT sample. The average value of the gap is, of course, just about the same. We can go a little further and ask, where is this disorder mostly located? So here I'm presenting histograms. These are of the overall band gap. This is the edge of the valence band relative to the Fermi level. This is the edge of the conduction band relative to the Fermi level. And this is for the CVT crystal on the top and for the flux crystal on the bottom. And what you see is that most of the disorder in the band gap actually comes from the valence band edge. Okay, good. So here's a summary of this part. We see that each of these defects produce donor states and acceptor states respectively. And if you look microscopically at the gap that this material presents for an optical experiment, it's incredibly disordered. So the question then to ask is, do you see any signature of this when you do a simple optical measurement? And we did one of the simplest measurements you can do, which is to measure light emission from these materials. So what you do is you pump up this material, you create electron hole pairs, you wait for a little while, and if you have monolayer materials, then it's famously known that these materials have a direct gap, and so the electrons and holes can recombine and give out light. And we studied how much light comes out from different materials with different defect concentrations. So let me give you a little primer into the band structure, and Jean has already talked a little bit about this. So this is the top of the valence band. This is the bottom of the conduction band. The valence band in these materials is split by several hundred millivolts. So I haven't drawn the other value, which is well below here. The conduction band is split by a much smaller amount in these materials. The conduction band splitting is on the order of 50 millivolts or so. This has some interesting consequences. For example, if I take this material, which is the molybdenum-based TMD, then the spin structure at any of these values is the same for the top of the valence band and the bottom of the conduction band. And what this means is that this transition from this lowermost state from here to here is optically bright. So you have light emission. Now imagine I start with t equals infinity. At t equals infinity, I'm going to populate both the blue guy and the red guy equally. And half of these are bright, half of these are dark. As I start cooling it down, all of my electrons are going to be sitting here. And so I get more and more emission because the population of the bright guys is increasing, until eventually at low enough temperature, everything is bright. Interestingly, in the tungsten, this is exactly reversed. So the blue guy is down below, the red guy is up above. And so in the tungsten, what you expect is as you cool down, then you get trapped in this dark state, and you can no longer emit light. So you expect no photoluminescence at t equals 0. So here, that's once again this picture. And one of the things that defects do, especially point defects, is point defects can couple different values. So a point defect can transfer any momentum to an electron. And so what it can do is it can take an electron from the k value and send it to the k prime value. And this generically, and there's many different mechanisms by which it can do this, this kind of business is not good for observing an effect like what I talked about earlier. So we expect that the temperature dependence of the photoluminescence when I look at a clean crystal and when I look at a dirty crystal are going to be quite different from each other. And we wrote down a simple phenomenological model. I won't go into this. We just wrote down some transfer rates from going from one value to the other, and came up with some simple formula that we could fit our data to. So here's the data. So what we do is we measure the photoluminescence. So here's the photoluminescence response of molybdenum diselenide, tungsten diselenide, and we measure this as a function of temperature. And in moly diselenide, as you expect, it goes up with decreasing temperature. And in tungsten diselenide, only in the clean crystals, we see this physics. So in the cleanest crystals, the photoluminescence abruptly drops off exponentially at low temperature. In a dirty crystal, so this is a dirty crystal, you see this overall behavior that comes from the fact that there's just a huge number of events where electrons from one valley are being scattered into the other valley. I did not mention here, I don't know why it's not here. If you look at the absolute magnitude of the photoluminescence, we also find that the absolute magnitude of the photoluminescence is roughly proportional to the defect concentration that you have. So if you have a material that has 100 times less defects than another material, we get 100 times more light out of it. And you can sort of see this here. These are two crystals that are both not very bad, but you can see that the cleaner crystal just has a lot more light than the crystal that's not as clean. Okay, so this slide has too many words, but I think I've told you what I wanted to tell you. And in the last 10 minutes or so, I want to tell you about something that to us came as a big surprise, which is magnetism. So let's come back to this picture. So this is my chemistry picture. This is molybdenum 4D2. You expect this thing to be a vegetable magnetically. One up, one down, happy together, no magnetism anywhere. Now, in theory, many people have asked what happens if you put a defect in this crystal, and there are many defects one can hypothesize, or edges of nanoribbons and so on, which could be magnetic, but one doesn't expect the pristine material to have any magnetism in it at all. So now what we did, and don't ask us why we did this, I'll tell you that another time, is we decided to measure magnetism in these materials anyway. And the way we did it is with this very nice technique called muon spin resonance, and not many people know about this technique, so let me spend a minute explaining to you how this thing works. So the basic idea behind this measurement is the fact that a muon can decay with a short lifetime, and the decay product of the muon, which is a positron, can be measured with the positron counter. And due to the wonders of physics, we know that the direction in which the positron comes out is very strongly correlated to the spin direction of the muon. The famous experiments done at Columbia. And so if you measure positrons, if I have a sample and I measure positrons everywhere, then I can tell what the direction of the spin of the muon was by seeing where the positrons come out. So here's how the experiment works in practice. I have a muon beam which is polarized. It comes and it hits my sample. My sample could be magnetic or it could not be magnetic. If it's not magnetic, then the muon, when it comes in, it's going to stick with the same spin, and when it decays, it's going to produce positrons only in this direction. On the other hand, when my sample is magnetic, then the muon is going to precess around whatever internal magnetic field exists in my sample. After some time, the muons will decay, and they're going to decay and produce positrons. You have positron counters on all sides of this crystal. You measure how many positrons you get, for example, in this direction, compare it to how many you get on this direction, and from that asymmetry, you can say something about what the internal magnetic field is in my crystal. A beautiful way to measure magnetism. And in practice, what you do is you measure asymmetry. That's the difference in positron counts between this counter and the counter on the other side. And if your sample has an internal magnetic field, then you expect the muon to precess. And so if you measure that signal as a function of time, what you'll see is beautiful precession. And that precession is a gold standard of magnetism. There's no way to cheat the muons. Right? So there's something magnetic in the sample, and that magnetism will produce oscillations. And from the frequency of those oscillations, you can say what the internal field is in your crystal. You can go a little bit further. Imagine that you have a homogeneous magnet, so a magnet that's 100% magnetic. And then you put muons, then every muon that sits in your sample is going to see exactly the same field. What it's going to do is to have exactly the same precession. And so that's going to give you a signal that does not decay. All things in real life decay, but to first approximation, it produces a signal that doesn't decay in time. On the other hand, if I have a sample that's inhomogeneous, so here's my inhomogeneous sample, these muons are precessing, maybe other muons do not precess, and then what you expect to see is a smaller component. So by counting how many muons I see in my asymmetry, I can say what fraction of my sample is magnetic. Good. So here's molybdenum ditelluride, and here is the data. And here was the big surprise. If you go down here, this is at 5 Kelvin, we saw beautiful oscillations. And beautiful oscillations tells you that the moment in the sample is uniform. So moly ditelluride 2H semiconducting is a magnet. And we can tell from the size of these oscillations that about 40% of the sample is magnetic. It's not 100% magnetic, but that part of the sample that is magnetic has a nice homogeneous field. We measured this as a function of temperature, and you see goes down, and around 40 Kelvin, we stop seeing these coherent oscillations in the muons. We can extract back from the frequency of these oscillations what the internal field is that the muons are seeing. That's the field, 200 millitesla. 200 millitesla is not a small number. That's a good magnet. Here's the same data on moly diselenide. Once again, you see oscillations at low temperature. In the case of moly diselenide, these oscillations vanish around 100 Kelvin. And the internal moment is even larger, 300 millitesla. So some of you may not believe μSR because many people don't understand μSR, so they're very suspicious of things that they don't understand. So you can put it in a squid, which now everybody has one off in their lab. And you can measure just the magnetization in the squid. So this is zero field cooled. That is, you cool the sample in zero field and then measure the data while warming up. And this is field cooled in 10 millitesla field and measured while warming up. And OK, so it's magnetic. So this is moly diselenide. This is moly ditelluride. And you see that in the squid, you see the magnetism all the way up to almost 200 Kelvin. And if you go back to the μSR data, this actually corresponds quite well to what you see in the μSR data. There's a temperature below which you have coherent precession, but even above that temperature, you have moments present. And you can tell that by the fact that the signal damps out. So I can get into that more detail if you want. But these temperature scales make quite a lot of sense with what we see in the muons as well. And you can sit at the lowest temperature, and you can do a hysteresis loop. This hysteresis loop looks really funny because there's a big diamagnetic signal also in these materials. And so the diamagnetic signal gives you this overall line. If you subtract this line, you'll see a fairly nice hysteresis loop in these materials. OK, so now the question is, why are these things magnetic? They should not be magnetic according to the pristine material. One thing you might imagine is that you have some foreign junk in there. Transition metals, they might have iron or chromium or nickel, things that are magnetic. We've looked quite carefully with lots of different techniques, and there isn't anything there. And there isn't anything that can explain 40% of the sample being magnetic. Just no way. Now, we went back to our STM data, and now my student Alex started looking at these defects in these materials again. And originally, we were looking at liquid nitrogen temperature. And the reason we were limited to liquid nitrogen temperature is these things are semiconductors. If you cool them down too much, they become rocks, and then they don't conduct, and STM doesn't work anymore. So I convinced him. He was very unenthusiastic about this. But I said, let's look at those defects again carefully. And he, once again, so these are the same two types of defects, the metal vacancy, the chalcogen antisite. And if you look at the chalcogen antisite, and you measure carefully the spectrum on the chalcogen antisite for moly ditelluride, let me jump straight to this. Oh, OK. So I had my story upside down. We talked to a theoretical collaborator, Elton Santos at Queen's University. And he simulated this anti-side defect. He seemed to think that this thing would be magnetic. And indeed, if you look at the spin polarized density of states associated with this defect, you saw some nice in-gap state, which in his calculations was magnetic. And so we went hunting for this particular defect state, and voila, we saw a defect state. But in STM, of course, in this STM, we're not spin sensitive, and so I cannot say that there's anything to do with magnetism other than the fact that there's a state there. Good. Now, so this is more recently, what we decided to do is we need to really go to low temperature to nail this thing down, because at low temperature, everything becomes nicer, STM is nicer. So we found that the samples were insulating, and then there's another story which I won't tell you about, but we found that if you shine lasers at these things become conducting. So now we are shining a laser at this thing. The laser does nothing other than make it conducting. Take it from me. And now we measure these same defects, and you see that these defects have these beautiful patterns around them. Quite spectacular. And this is the same thing at 77 Kelvin. And really the difference is not so much that things have evolved with temperature spectroscopically, it's that our STM is better at lower temperature. So that's our sample. That's with the laser on. So here are these things, these interesting flower patterns. And if you look on a larger scale, they're everywhere. And if you ask what region of the sample do these flowery things cover? Is it 40%? Maybe, not bad. So I was very encouraged by this, and I said, well, this has got to have something to do with the magnetism. So I said, we need to know what is this flowery thing. And so one of the things you can do in an STM image is you can just take the Fourier transform to understand what wavelengths exist in this image. And so here is the STM image in real space. Here is its Fourier transform. These are the 6 atomic peaks. And all of this inner structure comes from the internal structure of the flower. And what we've learned is the following. Here is one of these flowers. Here is the Fourier transform. What we've learned is that in these flowers, there is a commensurate period of 5 atoms. So here is a model for what we see. The pattern that we see has a 5-atom periodicity in real space. It's centered around one of these chalcogen antisites, and it goes out for a fairly long region in space. This is in moly telluride. This is in moly selenide. Here I'm showing you that same frequency, that same wavelength in space. You see exactly the same wavelength, 5 atomic lattice constants. As of now, we don't really know why this thing exists. So in progress is we need to understand why is there this wavelength. Second, once you have such a wavelength, is it possible that this entire region of the sample is magnetic? If you imagine, for example, that this is associated with lattice distortions, the lattice distortion can locally change the charge state of the molybdenum, which can certainly give rise to magnetism, for example. And finally, question is, even if these things are magnetic, how do these individual regions interact with each other? And here we've thought about this a little bit. And what we know is that for the typical densities of electrons and holes that we have, just from RKKY, we would expect a ferromagnetic interaction over the scale that we see. So this is a little bit of still unfinished work, but I think it's incredibly interesting that these materials that I always thought of as boring old semiconductors are anything but boring. They're actually magnetic. And in the context of dilute magnetic semiconductors, there were many beautiful experiments done in the gallium manganese arsenide system. And perhaps this thing is also a dilute magnetic semiconductor. Wouldn't that be fun? Okay, I see that my time is up. So let me end by thanking my collaborators. Jim Hone has helped me a lot with growth and with all sorts of things. Tomo Yomura is really the expert on μSR, and all of these measurements are done with his help. I talked about Elton, who did theory. Katie Barmack did the TEM work. Chris Marionetti helped us also with theory. And Xiaoyang Zhu is our optics expert who we go to for help with optics. So thank you very much.
Okay, yeah.
Hi. So you mentioned that you saw these defects are magnetic in at least two materials, molybdenum selenide, diselenide, and molybdenum ditelluride.
Uh-huh.
Do you expect it to exist in most semiconducting TMDs, or?
So we actually have beam time to measure the tungsten-based ones. Yeah. So far we've seen it in all the molybdenum-based TMDs. We haven't studied the tungsten-based ones yet, and so that remains to be done.
I'm just curious about the fact that you were able to get an order of magnitude difference in the quantity of defects between the CVT and then the flux method. What do you think are the primary reasons why you get significantly fewer defects in the flux method?
So one simple difference is just the amount of time and the temperature at which the reaction is run. So the flux reaction is run at a much higher temperature, and it happens much slower. And sort of, if you ask me, I would say slow cooking is better cooking, and so maybe that's the reason, but that's not a real reason. So yeah, so that's the extent of my knowledge. Yeah.
So when you eliminate the sample with the laser and you see that to be conducting, is it possible that you are somehow heating the sample with that?
Yes, you do heat the sample by a couple of Kelvin, but the heating is negligible. So we typically do the measurements around 15 Kelvin. Below that, even with the laser, doesn't help. And when you turn the laser on, it goes up to about 17 Kelvin. But yeah.
So for the for intrinsic doping of like polydisulfide, it's believed that there are some like vacancies like related to the like anti-doping intrinsically. So what can you comment on that? Like in this case, for example, you say the metal size corresponding to the donors.
So we have measured CVD samples where we have seen chalcogen vacancies. And it's a good question as to if you exfoliate bulk crystals, whether in that process you will also create chalcogen vacancies. That's a question that we have not answered yet. But everything that I've shown you here is that you don't need chalcogen vacancies. There are plenty of other things that exist in the crystal. And I think that the chalcogen vacancy stuff, I'm not saying that it's not important, but it's a little bit of a myth in the literature. Yeah.
Okay, so last question.
Oh, one last question. You said you cleave these in high vacuum.
Uh-huh.
How do you accomplish that?
Oh, it's fairly simple. These are van der Waals materials. So you take a crystal, you glue it down on a surface, and then you glue a little stick on the other side of the crystal, and then you just whack the stick. And so it just breaks the crystal in two. And
How do you get that done in vacuum? You do that all with the manipulator?
yeah. So you can buy a thing called a wobble stick, which is like a little hand inside vacuum. And yeah, it's, all the beautiful STM results are all done by stick whacking. That's a requisite procedure. Yeah.
Okay, great. So there's a lot of questions about the defects, and but in the interest of time, we should move on. So let's thank Abhay again for the very nice talk.
Thank you.